Hi, and welcome back to SpecterAI. I'm Specter P. Before we begin, please subscribe to the channel. It takes just a second to do, it's free to you, and helps us tremendously in posting new videos for you. In this lesson, we examine one of the most powerful real-world attacks on quantum key distribution, known as the detector blinding attack. This attack does not target the quantum states themselves. Instead, it exploits the physical weakness of real avalanche photodiodes, allowing an adversary to force them out of the quantum regime and into fully classical behavior. We will begin by reviewing how ideal detectors are expected to operate inside a quantum key distribution receiver. We then compare this ideal model with the actual behavior of real hardware, which can be driven into a blinded state by strong, continuous light. Once the detectors are blinded, we will see how an adversary can control when clicks occur by sending tailored bright pulses, and how this enables a complete intercept and resend strategy that produces almost no observable increase in the quantum bit error rate. Finally, we will examine why the security proof fails under this attack, how the entropy estimate becomes invalid, and what countermeasures are required to protect real systems. Before we examine the blinding attack itself, we begin with the ideal detector model that all quantum key distribution security proofs rely on. In the standard framework, Bob's detectors operate in Geiger mode, where a single absorbed photon is sufficient to trigger an avalanche and produce a binary click. The probability of a click depends only on the quantum state arriving at the detector and on the intrinsic efficiency of the device. The detectors are assumed to behave as ideal single-photon sensors, and they do not respond to classical optical power in any meaningful way. Under this model, any attempt by an adversary to gain information about the key produces an increase in the quantum bit error rate, which the protocol detects during parameter estimation. Real quantum key distribution detectors are avalanche photodiodes, and they do not behave like the idealized single-photon sensors assumed in the security proof. Avalanche photodiodes operate in two fundamentally different regimes. In Geiger mode, which is the intended operating regime for quantum key distribution, the detector is biased above its breakdown threshold. A single absorbed photon is sufficient to trigger a full avalanche, producing a clean binary click. This is the single-photon sensitivity that the protocol depends on. However, when strong continuous light is applied to the detector, the avalanche photodiode leaves Geiger mode and drops into linear mode. In linear mode, the device no longer behaves as a quantum detector. Instead, it responds proportionally to the optical power it receives, just like a classical analog photodiode. Individual photons no longer trigger avalanches, and the detector loses all quantum sensitivity. The transition between these two modes is the physical mechanism that enables the detector blinding attack. By forcing the detector out of its quantum operating regime, an adversary can control its behavior using bright classical pulses. This image shows how Eve controls Bob's clicks under blinding. Once Bob's detectors have been driven into linear mode, they no longer respond to single photons from Alice. Instead, they behave as classical threshold devices that fire only when they receive a bright optical pulse. This change in behavior allows Eve to take complete control of Bob's detections. Eve begins by measuring every incoming photon from Alice. She chooses her measurement basis in exactly the same way Bob would have chosen his basis in the protocol. Whenever Eve obtains a definite bit value, she prepares a bright, classical pulse and sends it into Bob's receiver, but only when her basis matches Bob's basis. Because the detectors are blinded, these bright pulses force exactly one detector to click, either detector 0 or detector 1. The outcome is entirely determined by Eve, not by the original quantum state that Alice prepared. When Eve's basis does not match Bob's basis, she simply sends no pulse. Bob interprets this as a photon loss rather than as an error. As a result, the quantum bit error rate remains low and appears completely normal, even though Eve now knows every raw key bit that Bob records. When avalanche photodiodes are forced into linear mode, they stop acting like true single-photon detectors. Instead, they behave like classical analog devices that fire, only when the incoming optical power exceeds a threshold. Eve takes advantage of this by sending bright pulses whose intensities she can tune precisely. If she sets the power just above the threshold for one detector but below the threshold for the other, she can choose exactly which detector fires. That makes Bob's measurement outcome fully deterministic. What used to be quantum randomness is now replaced entirely by classical steering under Eve's control. So, how much power does Eve need to force a click? Now that we understand how a blinded detector behaves, let's look at how much optical power Eve actually needs to force a click. A photodiode produces a current that's proportional to the optical power hitting it. That relationship is set by the detector's responsivity, and every detector also has a threshold current. Below that level, the circuitry reports no click, and above it, the detector fires. When the detector is operating in a blinded classical mode, this threshold becomes extremely sharp. Anything below the threshold gives no click at all, and anything above it produces a deterministic click. So Eve's entire goal is simply to exceed that threshold. Let's work through a real example. Suppose the detector responsivity is 0.8 amps per watt, and the threshold current is 0.32 milliamps. If we divide the threshold current by the responsivity, we get a threshold power of about 40 milliwatts. That means any pulse below 40 milliwatts will be ignored, and anything above 40 milliwatts will always produce a click. So for instance, if Eve sends a bright classical pulse of 50 milliwatts, she's comfortably above the threshold. The blinded detector will fire every time, and Eve can force Bob's outcome with perfect reliability. The graph on the right makes this behavior clear. Below 40 milliwatts, the click probability stays at 0, and as soon as the power crosses that threshold, it jumps instantly to 1. This is exactly why detector blinding gives Eve such precise control over Bob's raw key bits. Now, let's take a look at why the quantum bit error rate stays low during the detector blinding attack. Even though Eve is actively attacking the system, Bob doesn't see anything suspicious. Here's why. First, Eve only forwards a pulse when her measurement basis matches Bob's. That means the only time Bob gets a detection event is when Eve already knows exactly what bit he will record. Whenever the bases don't match, Eve simply sends nothing, and because Bob is blinded, that mismatch doesn't show up as a bit flip. It just looks like normal channel loss. So Bob's sifted key ends up being a perfect copy of Eve's classical bits, with no spike in QBER. The only thing that increases is the number of losses, which most systems don't treat as a security alarm. This is why intrusion detection that relies only on QBER completely fails. The attack suppresses errors, replaces them with loss, and keeps QBER deceptively low, while Eve learns the entire key. This graphic compares what BB84 is supposed to look like with what actually happens under a detector blinding attack. On the left is normal BB84. Bob's detectors operate in true Geiger mode, so clicks come from single-photon avalanches. Basis mismatches create random bits, and those errors show up directly in the QBER. Noise and mismatched bases naturally produce an error rate, and if someone tampers with the channel, QBER rises. Eve can only gain partial information, and privacy amplification is designed to remove it. On the right is the blinding attack. Eve forces the APDs into classical linear mode, where they stop acting like quantum detectors and behave like simple power comparators. When a basis mismatch occurs, Eve sends nothing. Bob doesn't record an error, he just sees a loss. Because of this, errors stay tiny and QBER remains deceptively low even though Eve is in the middle of the channel. Bob's sifted key ends up closely matching Eve's classical bits. Privacy amplification can't fix that because it starts from a completely wrong entropy estimate. This is the core vulnerability. The protocol still looks healthy on paper, but the detectors are no longer operating in the quantum regime. Here is why privacy amplification fails in blinding attacks. Privacy amplification is only as strong as the information you feed into it. The protocol assumes that Alice and Bob know the true QBER, that QBER accurately reflects how much Eve has learned, and that the amount of compression in the final step should scale with the estimated level of eavesdropping. In a normal BB84 run, that logic works. More errors mean more Eve, so you compress harder. Fewer errors mean less Eve, so you keep more of the key. Under detector blinding, that entire model collapses. Eve suppresses errors by forcing Bob's detectors out of the quantum regime and into classical linear mode. Mismatches that should produce errors are silently turned into losses. As a result, Bob measures a very low QBER, but that number is completely wrong. He believes Eve has almost no information when in reality, she knows nearly every bit. This leads to an error cascade. A wrong QBER produces a wrong entropy estimate. A wrong entropy estimate drives a privacy amplification step that compresses far too little. And at the end of the pipeline, the system outputs a key that Eve still fully knows. This is the central vulnerability. Privacy amplification hasn't failed as an algorithm. It's doing exactly what it was told to do. What failed is the assumption that the detectors were honest quantum devices. Once Eve blinds them, the entire security analysis is built on the wrong foundation, and the final key is compromised from the moment it's generated. The first real detector blinding attacks were demonstrated by Lydersen and colleagues in 2010 on fully commercial QKD systems. By shining continuous wave light into Bob's avalanche photodiodes, they forced the detectors out of Geiger mode and into classical linear mode. From that point on, Eve could send bright pulses and deterministically choose which detector clicked. Crucially, the QBER didn't budge. Even across 20 to 60 kilometers of telecom fiber, the systems reported normal error rates and normal key throughput. The operators saw nothing unusual. The entire attack required less than a milliwatt of optical power, and it gave the researchers complete remote control over Bob's measurement outcomes. This experiment proved that detector blinding is not a theoretical vulnerability. It is a practical exploit that can fully compromise deployed QKD hardware without triggering any alarms. Detector blinding attacks don't require large amounts of power. Experiments consistently show that only a few hundred microwatts of continuous wave illumination are enough to force avalanche photodiodes out of Geiger mode and into classical linear mode. Once the detectors are blinded, Eve only needs to increase the optical power slightly, usually between half a milliwatt and about 1.2 milliwatts, to trigger fully deterministic clicks. Different detector modules shift these thresholds a little, but the variations are small. The attack works reliably across manufacturers, and it doesn't require fine-tuning. The power tolerances are wide, and the detectors remain stable in the blinded state across tens of kilometers of standard telecom fiber. These ranges line up exactly with the theoretical power curve we calculated earlier, and they explain why detector blinding attacks are so practical. A simple telecom laser can produce these power levels effortlessly, making the attack easy to execute with inexpensive equipment. The defenses against detector blinding focus on restoring honest quantum behavior inside Bob's receiver and preventing Eve from forcing the detectors into classical linear mode. The first layer is hardware monitoring. Photocurrent sensors continually watch the incoming optical power and can detect when a bright continuous wave signal is being used to blind the APDs. Power watchdogs reinforce this by triggering alarms whenever the input exceeds safe bounds. Next, randomized detector efficiency makes the blinding thresholds unpredictable. Since Eve relies on precise power levels to force clicks, changing the detector gain prevents her from knowing which pulse intensities will produce a response. Variable gate timing achieves the same effect by altering the electrical conditions under which the APD fires. Optical power limiters provide a final safeguard by physically clamping any bright pulse before it can drive the detector out of Geiger mode. At the protocol level, measurement device-independent QKD eliminates this vulnerability entirely. In MDI-QKD, the detectors are no longer trusted components. Even if Eve controls them completely, the security of the key is preserved. This architecture removes detector side channels altogether and represents the strongest long-term defense. With these countermeasures in place, modern QKD systems can reliably detect, resist, or neutralize detector blinding attacks. Let's wrap up with a summary. Detector blinding attacks work by forcing avalanche photodiodes out of the quantum regime and into classical linear mode. Once that happens, Eve can steer which detector fires using bright pulses, replacing genuine quantum randomness with classical control. During the attack, QBER stays deceptively low because basis mismatches show up as loss rather than errors. Bob has no indication that anything is wrong. This feeds directly into the privacy amplification step, where a false entropy estimate causes the system to compress far too little, producing a final key that Eve still fully knows. These aren't theoretical vulnerabilities. Real experiments have completely compromised commercial QKD systems over tens of kilometers of fiber using less than a milliwatt of optical power, all while reporting normal error rates and normal key throughput. Today, modern countermeasures can detect or prevent these attacks. Photocurrent monitoring, detector efficiency randomization, and measurement device-independent QKD eliminate the side channel and restore provable security. This concludes our walkthrough of how detector blinding works and how QKD engineers defend against it. Thank you for watching. If you found this video helpful, make sure to like and subscribe so you don't miss the next deep dive. Subscribing really helps the channel. Visit SpecterAI.ai for hands-on quantum security labs and real-world exercises you can start right now. You can also check out our full series of books on Amazon to go even deeper into quantum cryptography, attacks, and defenses. Leave a comment below and tell us what you want to learn next. We read every suggestion. Thanks again for being part of the channel. We'll see you in the next video.